Welcome back. We're going to talk a little bit more about lists. Let me just start with a quick review just to make sure that we remember all the different pieces from the last few lectures. So let's start at the top here. I can initialize or define a list by having the name of the list, the variable on the left-hand side of the assignment operator, and on the right-hand side is an open square bracket, a closed square bracket, and a comma delimited list of elements. In this case, they're strings, of course, 5 of them. They can be integers, they can be floats, they can be booleans, they can be, as we already saw, a mixture of them. Okay. So this list has 5 elements indexed from 0 to 4. Okay. I can access elements using the square bracket operator. Sometimes I'll refer to that as sub, L sub 0, L sub 4, L sub 5, or just L0. So here I'm tapping into the list called L, that's of course that, and then the 0th element, which is A. So when I print L sub 0, I get A. When I print L sub 4, I get the last element. Again, we're starting to count at 0. Always be really careful with that off by 1 error. And of course, if I try to access the 5th element, which doesn't exist, I simply get an error. Okay. So I can define a list, I can access a list, I can rewrite a list. Or elements of a list. So L sub 1 on the left-hand side here is referring to that element, and then I'm going to reassign that to be the string X, and now if I print the string, I get AX, CDE. Everything's the same except that. So you can think about these L sub 0, L sub 4, 5, and 1 as simply as variables. So if I just simply had variables in all of these positions, I don't think anybody would look twice at it. It's just that we are now referencing individual elements of a list using that index operator. I can, of course, do computations. So in addition to printing things and assigning them, I can simply treat them like variables. So if I say S is equal to L sub 0 plus L sub 1, I'm going to do that, of course, must be string concatenation because those are strings. And of course, S is now just the string AB. Defining, accessing, assigning, and using in expressions elements of the list, just as if they're variables. We just have to specify the name of the list and then which position do we want to tap into. All right, now, so it does seem like lists are sort of like all other variables, and they almost are, but there's one little catch here, and we have to understand that. And it's going to turn out to be really important down the line when we talk about objects and classes near the end of the class. So let's just go ahead and do it right now. By way of reminding you, let's look at this little bit of code. And if I have a variable, no list anymore, just a variable, x equal to 5, and I assign y to be the value of x. What is the value of y, please? It's 5. Of course it is. That evaluates to 5 on the right-hand side of the assignment operator. Y is now 5, x is 5. Importantly, y is not x. Y is the value associated with x. So to see that, let's look at the rest of the code. If I print x, what will I get? Of course I get 5, right? Because that's just this value. All right, y equals y plus 2. What is this statement going to do? It's going to take the current value of y, which is x, which is 5. So y is 5, add 2 to it, and reassign y to that value. So when I print y right here, what am I going to get? Good, 7, of course, because I've just assigned it. Now, when I go to ask for the value of x, what do I get? Think about it for a second. If you're not sure, go ahead and pause the video and think about it. Well, there's sort of 2 options that you may have said. You may have said 7 because I reassigned y to be 7 and y is equal to x up here. Or you may have said 5 because 5 is the original value. And of course, it is 5. And the reason is that here, this is not really y is being assigned the value of x. So that when I change the value of y, I'm not changing the value of x. This is simply the value. It's a synonym for the number 5. So whether this had come from y equals x, or y equals 5, or y equals 2 plus 3, or y equals anything that evaluates to 5, doesn't matter to me. So when I change this variable, I do not change this variable up here. Okay, so importantly, y and x are completely separate variables and they don't know about each other. Okay, and we've seen this before. I just want to reemphasize it, and now you're going to know why, because now we're going to ask what happens when we do something similar with lists. Okay, so let's play the same game. X is equal to the list, square bracket, ABC, comma, delimited, 3 elements, 0, 1, 2. Y is equal to x. So now y is going to be assigned to be the list ABC. Same thing as before, right? No problem. Lists and variables or integers and strings are all the same. And what is this line of code going to do? It's going to reassign the 0th value of the list y to be d. So up at this line of code, y was ABC. After this line of code, it's going to be dbc. So if I print y, I get dbc. Good. Now, let's play the game. What happens if I print x? Now, two possibilities, right? X is still ABC because this is simply saying y is the list and x is the list and they have nothing to do with each other. Or maybe not. So what would you like? You would like it to act like numbers. You'd like it that x is equal to ABC. But in fact, it is not. When you, on this case with lists and eventually with objects, when you assign y to be x and you change y, you also change x. Okay, why is this? Why is Python giving me a hard time about it? Well, they're not giving you a hard time. As it's going to turn out, and I'm going to explain in a second, lists and more complex data structures are stored a little bit differently than integers, floats, strings, and booleans. And this is really important, and you can see why. Because when you make this assignment operator and you change y, it has the side effect of making a change to the variable that you assigned it to. That's a little dangerous, and so now we have to understand this. So why is it when x and y were integers, there was no overlap or crosstalk between them, but when they're lists, they are. So let's see why. Okay, so let's go back to the picture that we originally had when we assigned a variable x to be the number 5. In memory somewhere is a little cabinet with the number 5 in it and a label on that cabinet that says x. Okay? But with a list, what you're actually storing is not the list itself. It is an address to a list. Okay? So what do I mean by that? Here are the contents of the list, right? Content, ABC, ABC. But what x is associated with is not, as you can see here, that list itself, but it's something telling you where the list is being stored. It is the address in memory of where the contents are. There's a level of indirection. And what that means is that when I say y is equal to x right here, y is actually being assigned the address associated with the same list associated with x. This number, by the way, is just some number. It's just a representation of memory. So don't worry about what the number is. It's arbitrary. Think of it as sort of an address. So what does that mean? So look at what happened after I defined x to be ABC and I defined y to be x. There's only one list in memory. Now, if these were numbers and I said x is equal to 5 and y is equal to 5, there'd be two spaces in memory, x, 5, y, 5, no crosstalk between them. But with lists, and more generally with objects, which we'll talk about in a few weeks, you are storing an address to a list. So there's only one version of the list. So when I say y equals x, y and x are the same thing. And now you can see in this picture why when I change the 0th element of y, I changed the 0th element of x. Because I went to y, I went to this address, I modified this list, and that means x and y are now both pointing to the same modified list. Okay? So that's an important distinction to make, and it seems sort of like it's an inconsistency, but it's not. The reason we do this with these data structures is they sometimes can get very big. And if they get big, we want to have efficiency by storing these memories, and then we are going to have the ability to literally create a copy of it, and I'll show you that in a little bit. Okay, so that's why we're storing these addresses, because they lead to efficiency of implementation, particularly when these lists get very large. So now you can see what happened. I created a list. I created essentially another copy of the address of the list. So again, when I change y, I change the contents that y points to, which x always points to, and now I have this behavior, which is different for numbers, booleans, integers, and floating point values. Okay, good. So this concept of storing an address is going to come back to us again and again and again down the road. But it's important to understand that we have a slightly different way. Although we've treated them like variables, they're stored in a slightly different way. So there's a subtle difference between them. And we just have to sort of hold on to that. And I'm going to show you eventually how you can break that. When you make copies of a list, you can literally make a copy of it. All right? So let's pick it up in a few minutes. We're going to keep talking about lists for a couple more lectures, and then we'll move on to the next topic. I'll see you in a little bit.